Hey everybody, it's Ripley. I'm back again. We're going to talk about section 7.2. Excuse me, I'm parched, which is slope direction fields and Euler's method. It's really two little mini lessons. Now, I'm going to mess with something here. Just a sec. Watch this. If I do y equals x plus y plus 1, whoops, let's do y prime. Is this a differential equation? Well, it's an equation. That's a start. It's got an unknown function, y. It's got an unknown, and it's got at least one of its derivatives. Guess what? We have a differential equation. That's fabulous. So here's what we're going to do. I have no idea what solutions to this differential equation look like. Really, hitherto, unless they gave us a solution and told us to prove that it was a solution, we have no idea how to solve for a solution. Okay? But I'm going to show you how they did this. And we're actually going to do it together. So watch this. I'm going to figure this guy out. I'm going to figure out, at least, I'm going to get a feel for what the solutions look like. So what I'm going to do is I'm going to use my fancy schmancy graph paper. 1, 2, 3. I'm going to call this 1. I'll call this 2. Call this 1, 2. 1, 2, 3. And when I ask you to do these, 1, 2, 3, I'm going to tell you to put them on something that looks like this. Unless I give you the Cartesian plane, the specific Cartesian plane, 1, 2, 3, -2. I want you to do a -2 to 2 on the y, -2 to 2 on the x. Now, watch how this works. I'm going to change color of my pen here so we can see what's going on. All that you do is, you can think about it as a crazy coordinate tree. I put my points in here. And I'm only going to do a couple of these because I'll drive you guys crazy if I do too many of them. And then I'm going to put my points in here, and we're going to put the slopes on this slope field or this direction field. So let's start with the easy, just like we always do. Let's start with the origin. If I stick 0, 0 in here, do you agree that I get 1? Which means that at the origin, I have a slope of 1, right? If I plug, let's go 1, 0 in there. If I plug 1, 0, that means I stick a 1 in for x, a 0 in for y, and I get 2. So right here, I get a slope that looks like that, right? If I stick 0, 1 in, well, let's see what happens. 0, 1, 0 in for x, 1 for y. Notice, I guess I jumped on it with the 0, 0. You just stick, wherever you see an x, put a 0. Wherever you see a y, put a 0, right? In this case, wherever you see an x, stick a 0. Wherever you see a y, stick a 1. So I get 2. At 0, 1, I end up with the same slope of 2. All right, how about -1, 0? Stick a -1 in for x, a 0 in for y, you get 0. So this guy's right here. How about 0, -1? Well, wherever you stick a, or wherever you see an x, stick a 0, -1 for y, plus 1, and I get 0. Now, careful. The reason we're going to do a bunch of these is because we really want to be able to see this behavior, and then we'll talk about sort of some patterns that we see. Now let's just do this together without me insulting you by doing all of them. If I stick 2, 0 in here, 2 for x, 0 for y, and I get a 3. So let's see, that's going to be about a 3, right? If I stick 0, 2 in, don't I also get a 3 for the same reason? 2 for x, 0 for x, 2 for y, and I get a 3. If I stick a 1, 1 in here, 1 plus 1 plus 1 is 3. So that's going to be a 3. I'm just eyeballing these, by the way. 1, 2, 1 plus 2 plus 1 is 4. So these guys are starting to get a little steep, huh? So like that. Let's see, 2, 1. Well, it's the same as 1, 2, isn't it? So it's just going to be a 4. I get that guy. And then 2, 2 is a monster, right? 2 plus 2 is 4 plus 1 is 5. Let's see, that's going to be way the heck up there. So that thing's almost vertical. But look at what it does. Look at these guys. They kind of start to swoop down here, don't they? Well, let's play some more. How about 1, -1? 1 minus 1 is 0 plus 1 is 1, right? 1, -1 gives me 1. Let's make sure I am where I want to be here. Whoops. 2, -1. Well, 2 minus 1 is 1, plus 1 is 2. There's that guy right there. 0, -2. Well, 0 minus 2 plus 1. Ooh, that's a -1. Hey, that's new and different. That's novel, isn't it? How about 1, -2? Well, let's see. 1 minus 2 is -1, plus 1 is 0. Right? It's easy. I know I'm just walking you through the first one. I know I'm driving you guys crazy, but bear with me. 2, -2. 2 minus 2 is 0 plus 1. That's a 1. Now, let's see what's going on here. Do you see what's happening? It appears something funky is happening right here along y equals -x minus 1. But let's play some more. Let's see. -1, 1. That's -1. Plus 1 is 0, plus 1. Okay, that's going to be 1. Negative 1 plus 2 is 1, plus 1 is 2. So we got that guy. Negative 2 plus 1. Oh, that's a 0. Wait, negative 2. Oh, negative 2, 0. What am I doing? Negative 2 plus 0 plus 1. That's a negative 1. So we got this funky one again. How about negative 2 comma 1? Negative 2 plus 1 is negative 1, plus 1 is 0. Yeah, there's something definitely fishy going on along this line right here. Negative 2 comma 2, going to be a positive 1. Negative 2, 2. I got to make sure I catch this thing right, or you guys are going to yell at me. Now, negative 1, negative 1. Negative 1 minus 1 is negative 2, plus 1 is negative 1. Huh, that's kind of cool. How about negative 2, negative 1? Negative 2 minus 1 is negative 3 plus 1. That's negative 2. So down here, this thing appears to be pretty steep. Down like that, right? Negative 1, negative 2. That's negative 3 plus 1. That's negative 2 as well. And then negative 2 is negative 4 plus 1 is negative 3. Now, let's see if we can interpret what's going on here. It appears that all along y equals negative x minus 1. If I plug in any number along that, it's going to turn this guy into 0. Watch. If I stick a negative x plus 1 in for y here, I get x minus 1 plus 1. And all those cancel and become 0. So watch this. Look at what your eye wants to do with this. It's kind of cool. Let's do it with red. What happens is the function, let's say that my initial point for the function is at 2, negative 2. It appears as though this function curves down, levels off here, and then takes off. Watch. Steep, levels down, whoops, and then takes off again. See how these are going to get steeper and steeper as I go that way. Do one more. Comes down, levels off, takes off like that. It at least gives us an idea of what the solutions look like. Now answer this question. Are there any equilibrium solutions in this differential equation? What's an equilibrium solution? It's a solution, let's write this down because I know I didn't write it down. An equilibrium solution. Remember what it is? It's a solution that is of the form y equals c. So in other words, what we would see is a series of horizontal, these little segments would all be horizontal for some y equals c. Well, you may say, well, Ripley, along this y equals negative x minus 1, they're all the same direction. Yeah, but they're not all horizontal. So we don't have a horizontal solution or a y equals c solution, which is kind of interesting. Remember what those equilibrium solutions did in section 7.1. All right, so you're going to do a bunch of these. I also want you to look in your chapter and look at, they're cool because they can do them a lot more, well, clearly they're sitting right there in front of you. And they can do it at a lot more points than I can do it at. So check those out. We'll talk about them in class tomorrow. And I'll meet you guys over at Euler's method here in a couple minutes. All right, hey, everybody, welcome back. We're going to talk about Euler's method real quick. But we got to get over a notational issue first. Your author refers to f of xy as the diff EQ with x, y as the variables. It's just notational, and I realize it's confusing because that's a capital F, which implies from the past that we're talking about an antiderivative, but don't panic. So if we're dealing with this guy over here, you know how it's y primed. Whoa. It's y primed equals x plus y plus 1 with a new notation, and you'll see why we use this new notation. With this new notation, we just say f of x, y. The derivative part is equal to x plus y plus 1. Okay? Now, I'm going to show you something here. Let's say that I want to try and figure out a value of a function that from a differential equation where I don't know what the solution is. I have no idea, but I have its differential equation. Wow, this is really hard to write this low on this tablet. Sorry, guys. I'll figure it out. Let's see what we got here. Oh, that's going to be just awful, but bear with me. Okay, there we go. So, in other words, I want to figure out what y of some x sub n is, or f of x sub n. All right. Well, I can't figure out it exactly unless I can solve for the exact solution. Remember, these would be the solutions. All right, so I don't know what this is going to be. But if you think about it, remember back in the day when we first started playing around with differential equations, to have an exact solution, what we would need is an initial value, right? We need an x sub 0 and a y sub 0 to help us define any differential equation if we want it, or any solution to a differential equation. Now watch this. I'm going to do something clever here, and this is what Euler said. All right, let's say that our solution looks like that. And we're going to start at this point right here. This is going to be x sub 0. So this point right here is going to be x naught, y naught. That's going to be that guy. All right? Now here's what Euler said. He says, while I have no idea what the solution actually is, and sometimes you just can't analytically solve for these things. You don't have enough information. What he did say is, since I have its differential equation, I can figure out the slope of the tangent line at any point. So if I have x naught, and let's just look at this curve, even though I don't know what the curve itself looks like because I have the differential equation tells me what all of the slopes look like. So if I cruise over here, let's say 1, 2, 3, 4, and I'm going to call this x sub 1, and I go up here, look at what's going on. I know that the slope of this guy, this differential equation, is going to tell me that that's the slope of the tangent line at that point. All right, as long as I know that that point lives on the curve. All right, so this would be considered x1, y1. All right, if I move over 1, 2, 3, 4, this is going to be x2. If I have this point right here, all right, and I could draw myself a little thingy there, and I get x2, comma y2. Well, there's only one problem. Look at what we can run into. I don't know what these points are necessarily. I have no idea what they are. But what I'm going to do is, I'm going to do something really clever. Let's go out one more time. 1, 2, 3, 4. This is going to be x3. I know I bug you guys when I do too many examples, but just suck it up, buttercup. Just kidding. You guys know I respect you. All right? There's that one. Here's what Euler said. Euler said, screw it. I doubt that he actually said screw it. But what he said was, if we start at one point, watch what's going to happen. If I build a line segment that goes from x naught to x1, but has the slope of the line tangent starting at x naught, y naught, watch what happens. I get that line right there, don't I? That guy right there is built. Now, while this point is definitely not equal to x1, y1, this is going to be x1, comma, approximately y1, isn't it? Do you agree? Now, again, we are off the curve. We know we're off the curve. Well, we don't know that for sure. We could have gotten lucky and actually had this curve like wrap back around and hit it. But we know we think that we're off the curve. Let's put it that way. But watch what Euler said. He said, that's okay. We know what the slope of the line tangent to the curve is, so all we're going to do is cheat a little bit. We're going to come up here, and we're going to take the slope of this line, and we're going to move it up to a point that we know for sure. And we're going to build a segment from x1 to x2 that has this slope at x1, comma, y1. But now we're stealing this point instead. It's an approximation. It's Euler's method for approximating solutions for